In this video, we're going to discuss time. We're going to take mankind's view of time and we're going to break it down and show you that a problem we have with time is that we actually measure time with instruments made of matter, and that affects how we view time. And ultimately, what I'm going to show you is that it's not space that length contracts and it's not time that dilates. I'm going to show you that a model of matter, and to show you a model of matter that contracts and slows with velocity. And because our clocks are made of these models in matter, we inadvertently attribute that property of our clocks to the concept of time, the manifestation of time, I should say. This is Distinti's Rules of Scientific Acquisition. This is a supplement to those and how the rules of acquisition apply to time. Now, in the rules of acquisition, we use pictures to anthropomorphize different concepts. Like science is basically justice as an avenging angel, and that works because in science we don't know what the path forward is. We are blind. We don't know what the unified field theory is going to look like. All we have are instruments to measure our way, and we have logic to slice through all of the various proposed theories. That's what these spheres are. Over here, this is Mother Nature. Mother Nature is clean and simple. I didn't make her nude. AI did that, but I like it because Mother Nature has nothing to hide. We are the ones who avert our eyes. And in this picture here, she is musing herself over our human attempt to describe her mathematically. And the new anthropomorphization is of Father Time. I love the steampunk. This was done by AI. I really wanted a face that was more instrumented, but I could never get the two things working. So I chose this one for Father Time, and I chose this one for the Rule of Acquisition 39, the instrumentality trap, because I liked the face. That's really the face I wanted here. But whatever, with AI, you can never really get everything you want with it so far, at least what I'm seeing. So what we're going to do is we're going to break time down. We're going to split it apart. We're going to analyze it piece by piece. And so if you go to Wikipedia and you look up time and space, down here there's a part that said modern physicists usually consider it, meaning space, with time to be part of a boundless four-dimensional continuum known as space-time. Okay, but there are disagreements between philosophers and other stuff, whether this is actually a causal relationship or just part of a conceptual framework. And what they use is these, I think this is called a Minkowski diagram, I don't know, where they show space as it's moving through a timeline. And they typically show a light cone, which means a particle of light can from here. But this just makes things more confusing. Let me show you a simpler concept of space-time. Here you have the Earth as viewed from the North Pole. And the Earth moves through space over time. It also rotates. So if you take England here, and 90 minutes later, the Earth is going to rotate this much, and it's going to be this farther in space. Another 90 minutes, time is going to go on. This is a better concept of space and time, as an object moves through space and time. But let's assume we have a time machine. Let's say such a thing could actually be invented. And again, I love the steampunk science stuff. I love that the best. So you take your time machine, and H.G. Wells' time machine was set in England. That's why we chose England. And let's say you're going to take your time machine and you're going to go 90 minutes into the future. Well, in 90 minutes, your time machine is going to pop out in space here as the Earth moves from underneath you. So what you really should have had is not necessarily a time machine, but a space-time machine that would move and anticipate where the Earth would be 90 minutes into the future, so you could reappear at your laboratory in England, yada, yada, yada. So the conclusion we have to make here is if the space-time model were valid, then the timeline of a moving object would show it at different locations at different points in time. Okay, and we're going to analyze that in a second to see if that is in fact true. But let me just bring up this here. This is when I was doing the research, I found this. I finally understood why time even exists. And I finally understood, got his tenses wrong here. I don't know. This is one of the frames from that video. Is this really what physicists believe? Because this blows me away. Here we've got time in one dimension, and we got space in another dimension, and we are applying Pythagorean theorem to that. If this is what physicists are actually projecting, or is this just this guy's misunderstanding of what physics? I mean, this just goes to show how bad things are out there when we have tons and tons and tons of misinformation about space and time. Because you can't apply Pythagorean theorem to units, different units. They have to be the same units, even if they're orthogonal in space. So let's test this space-time continuum. I call this the Mount Fuji paradox. You have a clock at the top of the mountain, a clock part of the way down, and a clock further of the way down. You are standing with this clock here. According to our observations, this clock will be moving faster than your clock, and the clock at the lower down will be moving slower than your clock. So if the space-time continuum were a real thing, we should expect to see the top of the mountain disappearing as it passes into the future. And the clock at the bottom of the mountain would be passing into the past, disappearing from your view. In fact, where you are should just be one single little strip of this mountain that exists in your space-time. But that doesn't happen. The mountain doesn't disappear. Matter doesn't smear across space-time as one would expect according to the space-time continuum. So how do we resolve this paradox? Well, there's two ways. Okay, we could say that the space-time continuum is nonsense. We can say that, well, possibly it's not time that dilates. It's something else that's we're misattributing to time. And again, I'm going to show you that that, in fact, is a problem with the clocks, not the fact that time dilates. Or it could possibly be that both of the above are true. And this goes on to why we have the 39th rule of acquisition. All measurements are affected by the nature of the instrument, so do not attribute the nature and flaws of the instrument to the subject being measured. So let's look at the instrument and the flaws of the instrument. We're going to look at three kinds of clocks: a light clock, a mechanical clock, and an atomic clock. So let's look at the light clock demo first. So this is a light clock that is stationary. Now I'm going to speed this up because this is a long simulation. So what we have here is we have an emitter that emits a beam of light. I'm showing it as a ball because it's easier to show. That bounces off a mirror. Every time it reflects off the bottom mirror again, the counter goes up by 1. Now, this is the universal time. This is the what Einstein would call the relativistic time, but let's ignore this. This is just based on, using, that's reference for relativity. Okay, after 7 counts, the universal time has ticked 56 seconds. So now let me show you the clock in motion. Okay, so it took 2 seconds longer for this clock to count out 7 ticks. So this is what Einstein used as his demonstration of time dilation. But was light slowing down because the instrument was in motion? No, light was still moving at the speed of light. Did the instrument slow down because of time dilation? No, it did not. Nothing here was affected by relativistic effects. All we have here is a case where the clock was outrunning the light that's part of its mechanism. Nowhere in here do you have time dilation. Yes, the clock may length contract, but that does not affect its ability to count out the time. And so time dilation is not time changing, the flow of time changing. It's just an affect of our instruments moving through space, trying to catch up with their fields. And so, consider velocity. The clock is moving, okay? If time were dilating, then this t in the denominator would get smaller because time is passing slower. So if this denominator gets smaller, velocity actually increases according to this. And you say, well, no, it doesn't work like that. Time must be getting larger, and that would make the velocity slower. So you can't have, this can't be that our velocity can affect itself. This would be a circular definition. I have a big problem with a circular definition. Space and time are not affected by velocity. The object that's moving is affected by its velocity, but not space or time. That would be a circular definition. So this concept that time is the object that's dilating is a complete run-on bullshit nonsense. Okay, so there is no such thing as time dilation. Space and time are not affected by relativistic effects. That would be a circular definition. Space and time are independent of the objects moving through them. Say that again. Space and time are independent of the objects moving through them. And again, all we have is a race condition between light and matter. It's matter that is dilating. It's material processes are the things that are dilating. And let me show you the model of matter demo. This is the pretonic model of matter. What you see here are two pretonic charges. They are orbiting about each other. This system is effectively what an electron is according to ethereal mechanics. Pretons have to speed, and they move at the speed of light so that they can feed. The reason why they don't travel in just a circle is that they will be passing through space that has already been fed upon, and it's devoid of the medium. It takes time for the medium to flow back into the voids. So these particles are consuming the medium, and the byproduct of that medium, the waste product of that, are electromagnetic fields that keep them locked in this race. Now they are spinning through a spherical space. And right now they're stationary, but what I'm going to show you is when you put this system in motion, it's going to not only time dilate, it's going to length contract. So what you see here is this is a reference plane that's attached to the center of rotation. These red spheres are not actually the pretons. The pretons are in the tiny infinitesimal particles at the center of the spheres. The spheres are just there as a reference to show where the pretons are. These lines up here represent where the tops of the spheres would be at different velocities. So at white, that is the extent in the z direction going up that the spheres will pass through when they are stationary. When we get to half the speed of light, the tops of the spheres will not go above the yellow line. When we get to 3/4 of the speed of light, the tops of the spheres will not go above the orange. And when we get to 90% the speed of light, the tops of the spheres will not. And you can see them when we get there that they stop length contracting. So what I'm going to do now is I'm going to set us to 50% the speed of light. Okay, now watch. They're not going to go above the yellow. Because what's happening now, instead of having to spin to be able to feed, they are actually traversing upward. And so they have a component of velocity that allows them to feed on clean medium. And so they don't have to actually move to feed. So now if we go to 75% the speed of light, they're slowing down. You see their speed is slowing down. And the volume in which they're spinning through is now shorter. They're not going to go above the orange. Okay, that one looked like it did because it's actually a little closer to us. It's a perspective issue. Now we're going to go to 90% the speed of light. You see they're getting slower and slower and slower. And their motion will not go above the red here. If I get to 99% the speed of light, they're pretty much just going to be rolling very slowly in the plane. And this is where matter starts to decompose, because their motion through space is what generates the magnetic and electric fields. This protonic field is not an electric field. It's not really a magnetic field. Those fields are synthesized by the protonic field as this system rotates at the speed of light. Their motion through the medium is creating a field, but their actual material processes are at the bare minimum. This is barely even matter. If we go to 100% the speed of light, they basically cease to be matter anymore. No electric fields are being generated from this system. It's no longer an electron. This is the state of matter in a black hole. Matter becomes inert. And you'll find in the cosmology series that you'll find out that black holes aren't singularities. They're just Mother Nature's way of storing matter very efficiently. Very efficiently. That's all it is. It's none of this fantastic wormholes to other dimensions, or are we living in a black hole? It's just an efficient way to store matter. It's just that mundane. I'm sorry, but the truth is always not as exciting as fiction. So what we're seeing here is that because of the velocity of this system through the medium, the system begins to both length contract and its process is slow. This is what we used to call time dilation. It's not time. Time is not dilating. It's material processes. Material animation is dilating. And we've attributed that to saying, well, our clocks are slowing down, therefore time is dying. No, our clocks are just slowing down. Okay, this is a causal relationship. Relativity says length contraction and time dilation, but they do not offer a causal mechanism for which to say it's true. Thermomechanics has a causal mechanism to show that this is all material processes. It's nothing fancy, no spooky action for no reason, which is what time dilation or length contraction would be in relativity, because they don't have a model of matter. So because our instruments are made of particles affected by their motion through the medium, their operation will slow with velocity. It's not time dilation, it's process dilation, or you could use the term MAD, material animation dilation. So, but what can we know about time? Because we know it doesn't dilate, we know space doesn't contract. So what can we know about time? Well, in ethereal mechanics, we have reduced everything to three things: length, charge, and time. Everything, energy, electric fields, magnetic fields, all of that stuff can be reduced to these three properties, these three units. And right now we're on the verge of breaking charge down into more fundamental components. One of them is going to be a component of length, because it seems that the protons, their ability to consume space depends on their size. And so part of charge, which includes protons and ethons and all that stuff, we're going to break charge down. We're on the verge of doing that right now. So the question is, well, what's length and what's time? Well, my friends, I'm going to show you that we're still way too primitive in science to really understand what they are. So let me show you what we can actually know. So what we call time is based on a ratio of velocities. Let me explain. So the way we make a clock like this is it's got a pendulum, and this pendulum has a weight that can be slid up or down from a little screw on the bottom, which will change the period of this pendulum. So then what we do is we have an observatory that can precisely measure when the sun is perfectly overhead. And then what we do is we set this clock to noon, and then we wait a whole day until the sun comes perfectly up to noon again, and then we see if the hands are perfectly on noon. If the hands move farther, well, then the clock is moving too fast. And then so what we do is we lower the weight here to slow down the pendulum. And then we keep doing this and adjusting the pendulum so that every day when we observe noon, the hands are perfectly at 12. So all we have done is taken the period of the rotation of the Earth and divided it by the rotation of this pendulum. And what we said is the period of rotation of the Earth is n periods of the pendulum. This n is quite arbitrary. And then this basically can say, then we solve for the period of the pendulum, which is the second, is the period of the rotation of the Earth divided by a unitless number. So even though we have the unit of the second, we don't really know what time is comprised of, but we have created an arbitrary unit, which is in fact based on time. We just don't know what time is. And so that is what we're using. The same thing happens with space. We have the meter, and we use the meter as our unit of length. It's a completely arbitrary unit, but we don't know why space is even there. What's empty space? What is the whole universe? All we've done is divide up a piece of it and say we're going to call that our basic unit for scientific applications. Now, some people are going to say, well, why are we doing all the science when we really don't understand what we're doing? But that's the way technology progresses. See, we didn't have to understand what matter was or what fire was to build the wheel, build tools, or to heat our homes. We don't have to know anything. What we did is by trial and error, technology will advance. Technology is just the application of matter in physics to do things we need to do. And early technology had no bearing, no understanding of science whatsoever. Okay, but science goes forward. That depends on the advancement of technology. It's just now we're using science to help push technology. I hope you can understand that science and technology are two different things, but because of advancements today, we're kind of using science to help push technology, and they're interrelated now, but they were once two very separate things. Technology started since the beginning, and man started making tools. Science really pretty much began about, I don't know, the Roman days, maybe after the Dark Ages, I don't know, but it didn't start in caveman days. So science is a very new development. And some people can kind of bear these together, but they're not. This is independent of this, but this depends on this. So take with a grain of salt that the rest of the world still views time and space as a continuum, that they're somehow interrelated, which they're not. They have to be completely separate units in order for things to make sense. They have to be independent. They're not a continuum. But it doesn't stop them from blathering all kinds of mathematics onto them to come up with even more gibberish. Because, I'm not against math. I love math. But math is like anything else, like a computer. You put garbage into a computer, you get garbage out of a computer. You put garbage into a food processor, you get garbage out of the food processor. You put garbage into mathematics, you get garbage out. Gigo, garbage in, garbage out. This is the Patreon site. If you really want to support this effort, become a Patreon member. Our new cosmology series is only going to be offered to Patreon members at Passenger and above. So if you want to see the new cosmology series, you have to be a Patreon member. I'm not going to make that free. It's time people start helping this effort more. This is the repository. Everything that we release for free is here. Go to the YouTube channel and look at the intro video to show how to navigate this site. This is the YouTube channel. Again, go here to learn how to navigate the repository. This is the blog site. Great shout out to Sebastian for taking care of this. When I get more time, I will definitely spend more time here. I'm sorry, I am just squanched for time. Thank you. No more voodoo physics.